Hello everyone. In today's lecture, we'll discuss some theoretical aspects of reinforcement learning. In particular, we'll go into some error and suboptimality analysis of RL methods. We'll understand what it means to measure regret of an RL method and how that indicates the quality of exploration. And finally, we'll discuss some aspects of RL with function approximation. So in particular, this is what we plan to cover. So in the first module, we'll go into some notions of convergence and discuss some assumptions which are commonly made in RL theory, as well as discuss some background or preliminaries which will be needed for the next modules. The second module, we'll talk about analysis of fitted queue iteration, and we'll talk about what it means to have optimization error, sampling error, etc. in RL algorithms. Then we'll talk about how regret can be measured and analyzed in RL, and how that will help us determine the quality of exploration. And this will just be a primer and not really be anything more than that into regret analysis. And finally, we'll discuss when, with function approximation, can we still obtain efficient or convergent algorithms with RL. So you've known that in general, when you apply, let's say, deep Q networks or Q learning with function approximation, we don't know whether that would converge or not. It could diverge. But when can we still say things which are reasonable? That's the fourth part. And just as a disclaimer, this is not really an exhaustive coverage of topics in RL theory, and there's a lot of rich literature in RL theory which I would encourage you to check out if you're interested. And some resource links are present on the last slide of this lecture. Okay, so let's start with the first part where we would talk about different notions of metrics or evaluation metrics that we would use to see how good an RL method is. So the first metric is the metric of sample complexity. What it means is the number of transitions or episodes that you need in order to obtain a good policy, or let's say in order to estimate a Q function, in order to learn a good value function, etc. A typical result that measures sample complexity looks like what you see on the slide, where we would say that if you collected n samples or n transitions, where n is a polynomial is a function which is polynomial in states and the size of the state space, size of the action space, and the effective horizon, which is 1 over 1 minus gamma, then let's say you can say something like the Q function for a particular policy pi, that is Q pi, can be estimated to epsilon accuracy at all states and actions, which means that if your estimate of the Q function is Q hat by SA, then that is close enough to Q by SA on all states and actions. And something like this is typically used to measure how easy is it to infer, let's say, the optimal policy, or even, let's say, the Q function for a particular policy, assuming no exploration bottlenecks. That is, let's say you're given a data set, and that data set comes from somewhere. For example, it could come from a behavior distribution that is from a human demonstration, or come from the replay buffer of some other agent, etc. Or it could just be even like an online. It could just be a uniform distribution over all the state action pairs. Then how effectively can you use that to get an estimate of the Q function, the policy, the optimum policy, etc., without really talking about anything to do with exploration? That's what sample complexity typically measures. The second notion or the second performance metric of an RL method is this metric called regret, which is typically used for online RL methods. So let's say your RL algorithm produces a sequence of policy iterates pi naught to pi n. And what are these iterates? So in a typical RL algorithm, you would train your policy, and you'd use this partially trained policy to then run in the environment and collect some more data and repeat this process. So whichever policies that you're ending up running in the environment are these pi naught are indexed by pi naught to pi n. So let's say you did n time, you collected data n times using these policies, using each of the policies that you find during training. Then these are those policies that you collected data with. The regret in this case is basically aimed at understanding how quickly the algorithm converges to the optimum solution. So what it really measures is basically it's a summation over the performance of the best policy or the optimal policy, which is V star, minus the performance of policy pi I that you ran in the ith data collection phase. So essentially what it does is that it sums up this quantity over all the possible iterations or all the possible data collection episodes that you did. So in a sense, if your algorithm is good, what it should happen is that it should produce pi i's that are quickly equal to pi star, meaning that that there should be a small enough I such that pi I is close enough or equal to pi star. If that happens, the regret is small, and that also means that your algorithm is good. For a more visual description of this algorithm, let's consider this plot, which is basically showing a typical learning curve of our 3RL algorithms here on the screen. And let's imagine that the optimal performance is the horizontal line at y equals 1. So that's the optimal performance. And on this plot, the y-axis is the return or the performance, and the x-axis is the number of training steps. In this case, the area between the learning curve and this horizontal line y equals 1 and the y-axis is basically the region which is kind of indicative of regret. So what you would want is you would want this region to be as quickly as possible decay down to something very small, because then that indicates that your method, first of all, is converging to the optimal solution, and secondly, it converges at a good enough speed, meaning that it converges at a rate that is good, meaning that it is fast. And that's what you really want, because each sample costs in RL. No data collection is really free. And it's usually, as I said, it's used to typically measure how good an exploration algorithm is, or something like that. And what does a good result for exploration or for regret minimization look like? So, for example, one of the results, one of the kinds of results that we could hope for regret minimization is something that says that the regret as a function of the number of data collection steps or data collection episodes, which is the x-axis, is sublinear in n, which means that if you do n episodes, your regret grows at a rate that is smaller than n. It's not linear in the amount of episodes you did. What this means is that you are effectively converging towards the optimal policy, essentially, because if you don't do that, then you always are going to incur some regret at each step. So each of these terms that you're summing over are going to be non-negative or going to be positive, and so you're going to be incurring nil-linear regret. But if that's not the case, that means you're converging to the optimal policy quickly enough. So essentially what this tells us is that it tells us that if you run your algorithm for long enough, you would get a good solution. And more than that, it also tells us that the speed of the convergence of the algorithm is good. So ideally, you would want something that is like n to the which is also even stronger than square root of n. But typical algorithms or typical bounds look like square root of n. Okay, so those were the notions of performance metrics that we typically use in the analysis of RL methods. Now, what are the kinds of assumptions that we want to use? So the analysis of RL is somewhat challenging because it involves these different components. It involves an exploration module, it involves a learning module, and these have to interact in right ways. For instance, if you don't get them placed well together, you might end up losing on sample complexity because you might end up overfitting too much in the training phase, or you might end up collecting data from suboptimal policies. Either way, things can go wrong. So what has been done in RL theory is that people have often analyzed different methods under different kinds of assumptions. And those assumptions are good because they help us analyze a part of the problem without caring about what the other part suffers from, or without caring about what the other part looks like. Because otherwise, the analysis is somewhat too hard to really do it in general scenarios. So typically, the analysis breakdown happens as the works that analyze the entire RL algorithm, which means exploration as well as how you can learn from it. And there are methods that only analyze the fact that only analyze the learning part, where you assume that you're given data from an exploration policy, and how good are you able to learn from it, or how many samples do you need to be able to learn from it, which is the other sort of assumption, where you assume you have exploratory data. So, and these analyses often tend to analyze these things separately, or analyze only the one thing, assuming good things for the other part, because that just makes life simpler. So one of the assumptions that we would end up talking about even in detail in today's lecture is this assumption of a generative model. So what we want to do here is we want to remove the exploration bottleneck. So what is the assumption that we make? The assumption that we make is that the algorithm is given oracle access to sampling from the dynamics model of the MDP. So what it can do is that any algorithm can query any state action pair to the dynamics model and obtain one of the next S prime samples, or the next state samples that you would observe from the true dynamics model. So you assume sampling access to the MDP. What you can do with it, for instance, one thing you can do with it is that you can construct an empirical dynamics model that basically looks like p hat, where p hat of s prime given sa is given by the ratio, the number of times you observed or S prime corresponding to S and A when you queried the true dynamics model of the MDP, divided by the total number of times you end up querying S and A for the MDP. So this is sort of an estimate or an estimator for your dynamics probability, and this could be, for instance, an empirical dynamics model that you could, for instance, use to approximate the Q function, because this dynamics model roughly tells you what your MDP is, and hence you can approximate the Q function to the value function via planning. And the question is, for example, one of the questions we'll talk about in this lecture is how does the approximation error of this dynamics model affect the errors in the value function, meaning that p hat is not the same as p, so how does the difference between p hat and p affect the learned Q function that you would infer if you were to use planning for p hat. Okay, so for the last part of this first module, let's talk about some preliminaries. And a lot of these, I'll discuss basically two things here, which relate to something called concentration in statistics. And I'll present two lemmas, and both of these lemmas are taken from the RL theory textbook, whose URL is provided below. And I'll not go into the proofs for this in this lecture, but you should, if you're interested, you should check out the proof for this in the book or on the internet. And these are very standard inequalities that people use. So what's the goal in concentration? So the goal in concentration is to talk about how exactly, if you were to draw, let's say, n samples from a distribution. So let's say you have a random variable x, it has a distribution, you drew n IID samples for x. And let's say you try to now compute the average or the expected value of the distribution by taking the sample mean. So you drew x1 to xn, you compute the average average of these samples, and use that for use that as an estimate for your true mean of the distribution. If you do that, then how quickly does so the question that concentration tries to answer is how quickly does this sample estimate or the sample mean converge to the actual mean. So you want to talk about, for instance, what is the maximum divergence, or what is the maximum difference between the sample mean and the true mean of the distribution. And the concentration allows us to bound this divergence or bound this difference in terms of probabilities. So the first inequality, to be more formal, is this Heffding's inequality, which basically tries to answer the question that if you were to draw n identical and independent samples from a random identical and independent random variables which share the same mean mu, then the sample mean, which is x bar n, is close enough to the actual mean mu, meaning that the probability that the sample mean is more than epsilon far away from the mean mu is exponentially small. So as soon as you go far away from this mu value, it's less and less likely that your sample mean is going to be there. So it's basically sort of a probabilistic guarantee on how far away your x bar of n can be from mu. And this holds true in both directions. So x bar of n cannot be too much higher than mu, and x bar of n cannot be too much smaller than mu. And b plus and b minus are just the ranges for the random variable. So it assumes that you know that the random variable lies in a particular range in the worst case. So let's say it's a uniform random variable, which means it lies between 0 and 1. So what does this allow us? So it allows us to write down bounds on the sample means as a function of the true expectation with high probability. So these are not exact statements. You cannot really say that for every sample you would draw, this is true, because a sample can be arbitrarily out of what you have seen, and it can make the mean be arbitrarily large or arbitrarily small. But with high likelihood, as in if you were to draw these samples 10 times, with high likelihood, with like in like 99% of the times, you would find that the sample mean is going to be close enough to the true expectation. So these are bounds that hold with high probability. So for instance, the last line that you see on your slide says that with high probability, which is more than 1 minus delta, so delta is just a chosen number, we're saying high probability means probability more than 1 minus delta, and delta is small. Something like this holds, where what this means is the sample mean minus the true mean is less than the range of the space, the range of the values that the x variable can take, times a quantity that depends on 1 over delta, which is the chosen confidence, divided by 2n, where n corresponds to the number of samples you drew from your distribution. So if you drew let's say 10 samples, you would get a bound that is tighter than when you drew only one sample, because with more samples you'll converge quicker to the mean. So essentially, what it tells us is it allows us to use sort of so when we train RL algorithms, we really are in a setting where we don't know the true expectations because we have sampling error. We only see certain transitions once. We are not seeing the exact distribution. So in that case, such concentration inequalities allow us to bound the divergence against the true estimate, which you would have gotten if you were to use the true expectation. And if basically the high level sort of the key takeaway or the summary is that you can say that the average over samples is close to the mean, and this is a bound in that value. There are also more complex variants of such concentration inequalities, such as the one that you see on the slide right now, which talks about concentration for discrete distributions. So let's say you are trying to estimate a dynamics model in a setting where your states are tabular. So you have a finite set of states, finite set of actions, finite set of next states, and you're trying to estimate the probability density of next state given current state and current action. And that's a distribution. And you're trying to estimate using counts, as we saw on the previous slide with the generative model. In that case, you can still sort of apply concentration inequalities. You can develop them sort of inspired from the Hebding's inequality, which give us bounds that say that the total variation divergence, which is a probabilistic notion of distance between distributions, is not going to be too large enough. Or what it says here is that the total variation divergence between q hat, which is the estimated distribution, and q vector, which is the true distribution, the probability that this is going to be more than a certain value is exponentially small. So it tells us that we are kind of bounded in a small region around the true distribution. So we cannot observe samples that are too far away from this bounded region. And we'll use this version to obtain some bounds for the generative model bit that we'll discuss next. And we'll go into this in a bit more detail there. But the high level idea, even if you don't follow the exact equations here, is that these concentration inequalities allow us to basically bound how far away can our deviation be when we sample things as compared to the true mean, which is the quantity of interest that we want. Okay, that's basically it for part one.